All right, let's work on the next part of this lecture series on paleontology on the early primate and the early primate fossil record. But let's focus on dating. Like, how do you know how old something is? And we have a few different types like relative dating, absolute dating, and calibrated relative. We'll explain each one of these. So there are three basic dating techniques or types. One of them is relative dating, and this is where we can use the stratigraphic sequences in soil. If it's not necessarily disturbed to a great extent and the soils aren't mixed together, we have nice, clear sequences and layers of soil. And that would mean that the older soil has to be deeper in the earth, and then the younger soil in time has to be closer to our feet or closer to the surface. And so we could label each one of these layers A, B, and C. And the oldest one would be the deepest in the ground. The youngest would be at the top, and layer B would be in the middle. Uh, Layer B is younger than A, and it's older than C. And many early scientists, before the invention of things like radiocarbon dating, before 1955, they uh, they didn't know how old things were, as well as if you don't have, sophisticated equipment, you can take a bunch of artifacts or fossils and you can say, well, I found these fossils in layer A, I found these ones in layer B, and found these ones in layer C. I can line them all up. I can say, oh, that A is the oldest, C is the youngest, and B is in the middle. I don't know how old they are in terms of a calendar date. These fossils could be 50 million years old. They could be a billion years old. I have no idea. I just know that I can find the chronological sequence of the specimens, but not their age. That's the key. Absolute dating techniques are ones that usually give you a calendar date, and they're calibrated in some ways to use something like a proxy for time. Radiocarbon dating is one example. We can also use volcanic ash layers. We have a number of different sophisticated techniques that can look at, for instance, the decay of certain isotopes to tell us how old something is. When you find a volcanic ash layer, it's really, really important in the fossil environment because we can figure out how old ash layers are. Remember that a fossil is something and that has been fossilized, and all of the organic material is replaced with inorganic material. So you can't directly date those fossils because radiocarbon dating it doesn't go past that old, like billions of years. Matter of fact, radiocarbon dating only goes past maybe or only good up to about 60, 70,000 years, and you have to have organic material. If you don't have organic material, it's fossilized. You can't use that technique. Matter of fact, so volcanic ash layers, they provide a really good way to tell a fossil is older than or younger than something. So let's say we have a volcanic ash layer, and each one of these layers, A, B, and C, they're unique. They're unique eruptions that tell us about ancient volcanic activity. We can figure out how old they are in millions of years. That's what MYA is, plus or minus. Uh, in this case, in C, that volcanic ash layer dates 1.83 million years ago, plus or minus 210,000 years, because we do have error rates in our techniques. Any scientific technique has a known rate of error. Don't be fooled. This is always, anytime you hear a scientific technique, you should always be able to ask, what's the error rate? And then somebody should be able to calculate it if it hasn't been done already and tell you. So look at it. C, B, and A. You notice that C is the youngest and A is the oldest and B is in the middle. That's great because now you can confidently say, hey, my layers are unique layers and uh, it hasn't been disturbed. They've actually been preserved. Calibrated relative dating methods are methods where you actually have a technique that has been well studied that you can use as a way to establish an age marker for events. Many people do this when they find fossils that are legitimate, like if you find a fossil like a trilobite fossil is very popular. Um, if it's legitimate, that trilobite fossil is between 200 and 500 million years old because everybody that has found a trilobite fossil in all parts of the world have published their absolute dating uh, techniques and methods. And everybody who's found a trilobite fossil and they've dated material around in those soils, the numbers that they typically get are between 200 and 500 million years old. So if somebody finds a trilobite fossil and hands it to you, and it's a legitimate fossil, it's been verified, you can confidently say that the fossil in your hand is 200 to 500 million years old because it's been calibrated. I can use all the published material in the fossil record to establish a date for it. Now, the trilobite in my hand, it could be a billion years old. It could be 50 million years old. You will never know because it was taken out of the ground and you don't have anything to figure out how old it is with an absolute dating method. Exactly. Well, you could, but oftentimes that's not, how people encounter fossils in this way. Well, you get the idea, hopefully. A great thing you do with stratigraphy and soils or strata is you can actually create sequences. And then they have done this at a number of different paleontological sites. And you can have different sites, like here demonstrated site A, B, C, and D. You can have sites that are in a general area. And then researchers can create the maps of the stratigraphies and then compare them to each other. And some people can be doing different techniques because they might have different funds or they have different interests in research, and they can help you and share their information that they get from these layers, and you could use them. And so, biostratigraphy is a way to figure out, stratigraphic sequences through fossils. Tephra and litho, you're just looking at, different prefixes. Tephra is looking at, um, different ash layers, volcanic ash layers. Lithostratigraphy is also looking at different properties, different layers of rock. To quickly explain to you how radiocarbon dating works, you don't necessarily need to know how this whole process works. Um, but you need to know some general ideas about both how radiocarbon dating as well as uh, potassium argon, which is how we date volcanic ash layers. These are absolute dating methods. We'll show you kind of how this works. So radiocarbon is a really popular one. It's used today, but it's typically only in archaeology because one, you usually don't have organic material in specimens after 60 to 70,000 years, as well as our techniques and our technology are not very good at finding accurate dates using radiocarbon past, again, 60 to 70,000 years. So what happens is there are three different isotopes of carbon. Everything on Earth is a carbon-based life form. And so anything that was once living is made of carbon, and we have remnants of that carbon in there in those isotopes. And so the main isotopes of carbon are 12, 13, and 14. Uh, you know, uh, Two of them are stable, 12 and 13, and 14 is unstable. It means it actually decays. It actually loses bits and pieces of it. When you look at the actual component of the isotopic component in terms of percentage, a breakdown of anything that's carbon on this Earth, carbon 12 takes about 99% of carbon. Carbon 13 is about 1%. This is stable. It doesn't change, right? So if you have something that's 100 grams, it should have 99 grams of carbon 12, 99 grams of carbon 12, 1 gram of carbon 13, and then it actually has a very, very small, 0.001%, something like this, of carbon 14, but we can measure it. And so, plants are taking up uh, carbon through the atmosphere because carbon 14 is actually brought here by cosmic rays and it decays in carbon 14. And plants are getting carbon 14 from the cosmic rays, and the animals are getting it from sun exposure as well as consuming the plants and the animals, and we consume both of them. So you're constantly exposing yourself to carbon 14, you're uptaking it in your body. But once an organism dies, there's no more exposure to carbon 14, and so the abundance is fixed. And it naturally decays. Bits and pieces of that carbon 14 are lost. Carbon 12 and 13 is stable. It's not lost at all. It's retained and actually creates a nice measure for expectations because it's supposed to stay the same. And then after every 5,730 years, exactly half of that radiocarbon is gone. Um, and so uh, that would mean that it has a half-life of, again, 5,730 years, and every halving of that half-life, because this is a fractionization method, uh, then you're looking at another 5,730 years. So uh, you don't need to know all these details. I'm trying to explain it so when you have a question, it's fairly simple, both in your quizzes and your exam, that you do it by what you know. An important thing for you to remember is we never directly date fossils like using an absolute dating method. We have to use things around the fossil because the fossil, right, was once organic, but it's all gone. It's replaced by inorganic material, and we can't uh, use radiocarbon dating, for instance, directly on a fossil. There are some techniques that are coming out. Um, but what we oftentimes do is we use the volcanic ash layers that fall above or below a fossil. So let's look at some of the fossils here in this sequence or stratigraphic sequence. And we have tuffs. These are volcanic ash layers. And we figured out how old they are using a technique known as potassium argon. Potassium 40 as an isotope actually decays into an argon gas, argon 40, and then it tells us when the last time the rock has been heated, i.e., when was the volcanic eruption that created this ash layer, and that gives you roughly a date and time of when this occurred. So look at tuff A, B, and C, right? The oldest one is A, the next oldest is B, and the youngest is C. Both the way layers of soil are naturally put down, as well as you can see that the layers have been dated 1.8 to 2 to 2.6. So yes, they are not disturbed. They've been laid down and the sequences are preserved. Look at the fossil between tuff A and B. What we would do is researchers would say, okay, well, we found this fossil between tuff A and B. It dates between 2 and 2.6 million years. However, we think it's probably a little younger, closer to 2, because it's right underneath tuff A. For the fossil that's between tuff B and C, we can confidently say, hey, this fossil 1.8 to 2 million years. Some people might say, whoa, a 200,000 year gap, we don't really know. Is that the best science we have? Yes, because we can't directly date the fossils. We have to use something above and below it, and this is typically known as bracketing fossils or the bracketing method. If you didn't understand anything I talked about in terms of absolute dating techniques, this is the slide for you. This is also a really good review slide because it tells you exactly the main types of radiometric dating techniques that you'll probably encounter. One is radiocarbon, and this uses the isotope of carbon-14 and measures it to stable isotopes 12 and 13. It has to be done on unfossilized organic material. What it actually does is it measures the time since death, right? It's physically measuring the last time an organism died. So, for instance, if you were trying to radiocarbon maybe a piece of wood from furniture, it would tell you when that furniture was really built. It would tell you when that tree was cut down and killed to make and fashion the wood for that furniture, which may not have happened right after it was cut. The effective range, 50, 60, maybe 70,000 years with our technology, at least currently. Potassium argon, these are looking at the ratio between potassium 40, the isotope potassium 40, actually decays into an argon gas, argon 40. It's used on rock, volcanic ash layers that have been heated to a high temperature, and what it does is it measures the time since the rock was last heated, giving you an idea of when that volcano erupted in time. The effective range is 100,000 years, and the half-life of potassium argon is 1.25 billion years. And so you can look at things that you can date things effectively that are older than the age of the Earth. I gave you an example of calibrated relative dating when you can use the fossil record, which is the compilation of all the research that's ever been done, that you can use it to help you find out how old something is. Now, you can use other techniques, like, for example, I like to talk about this one, which is geomagnetic polarity or paleomagnetism. Um, what this does is it actually measures different um, magnetic fields in the earth that have been preserved over time. So when we look at soils that are really old, they actually record the magnetic field of the earth. And so when you think about like a compass, for instance, you pull out a compass and the compass points to north because it's measuring and locating our magnetic field. Now, our magnetic field is slightly tilted. And so if you took a compass that's trying to measure the magnetic field and you tried to go to true north, which is the point which actually divides the Earth into four quadrants, you would be about 11.5 degrees off because our magnetic field is on an axis. And when you think about global positioning systems, that's where you actually are dividing the Earth into four equal quadrants with some of these points, for instance. Um, in the past, this magnetic field, and even into the present, is actually moving. It's active. It's actually moved a little bit more. People are just reporting on it. So it's slightly shifting. There's a map here in the lower left that shows where it was around the time of Columbus in 1492, or when it was around where it was around 1200 AD. We have cores in the Earth that we can take to locate where the magnetic field was. Matter of fact, the magnetic field sometimes has switched poles where north is south and south is north. That would mean you pull out your compass, it's pointing to the South Pole, um, and all our maps would be wrong. Well, this hasn't happened for maybe a million years. I think the last time the poles have actually switched was about 900,000 years ago. But you can take a really big compass, which is basically what's known as a magnetometer, and you can bring that really big compass over and bring it over soils, and it will read the magnetic field of those soils. If all of a sudden you're going north and you've got your compass pointing north and you walk over a sediment and all of a sudden it switches to the South Pole, you are on some soil that probably is at least a million years old. And so this is only because people have figured out what each one of those layers, and every time the magnetic field has changed, right? So that is something that, you see, the ground truthing's been done where people have located and documented the stratigraphic levels and the magnetic fields associated with it, and people can go out there and locate them because all of the work has been done to calibrate it.